Hello, my name is Bruce McCluggage. I work in the faculty department here at Pikes Peak Community College. Today we're interviewing Andy Fletcher. Andy Fletcher is a mathematician, historian, just a philosophy of science guy that we've brought onto the campus here within the past week to a maxed out crowd in the theater here at Pikes Peak Community College. Andy gives classroom seminars not only in the US but in the United Kingdom and Canada, about 40 different countries around the world, and he's given this presentation I think about over 200 times. The presentation Andy does is to help students re-examine some of the scientific assumptions about truth and how the world operates, and some of those are pretty mind-boggling. He has a quote in his book from an astrophysicist, Sir Arthur Eddington. He said, "Not only is the universe stranger than we imagine, it's stranger than we can imagine." Andy, it's good to have you with us here today.
It's good to be here.
I'm sure you know that the Western world was rocked by this guy named Copernicus quite a few years ago, and we're still feeling the repercussions of that in our culture today. And yet right now we're in the midst of another kind of scientific revolution that makes the Copernican revolution almost look like a walk in the park. That scientific establishment as a whole still really hasn't fully absorbed that, and it's still emerging as we go. So enough of me, let's get into this right with Andy right now. Andy, here's our first question for you. What is it that you do? Just in your own words, explain to us a little bit about this 3-hour seminar that you had with us this past week.
Well, it can go anywhere from 1 hour to 12 hours. So the 3-hour version, I was jamming things in quite a bit. It was something of a challenge. The simple answer is that I go to schools that offer the International Baccalaureate curriculum around the world, and they have a course called Theory of Knowledge, which is abbreviated to TOK. So if I say TOK during our talk, you'll know what I'm talking about. Theory of Knowledge is kind of a course in epistemology, and when people ask me what TOK is, I'll tell them it's a course where at the beginning of the course they ask the students the question, how do we know what we know?
Which is the definition of epistemology.
There you go. How do we know what we know? How do we know that we can trust knowledge? How do we know that history is accurate, that it's real history? Same thing is true for all fields of human inquiry, for science, for mathematics, for literature, for linguistics, social issues, sociology, absolutely everything. And then at the end of the course, they answer the question, how do we know what we know, with the answer, we don't know how we know what we know. So it's a little open-ended and a lot of fun.
A little open-ended, huh? Okay. Tell us a little bit more. Why are you in particular so passionate about this topic? I mean,
well, I love most of the schools that I go to are international schools around the world. They're for students from all different countries. Their parents work for multinational businesses and diplomatic agencies and all the rest of that. So they are the most fascinating kids. They are the leaders of the next generation. They're the next generation of the world's leaders going to schools all over the planet. And they're bright and they're fun and they come from so many disparate backgrounds. They're just a lot of fun to be with. When talking specifically about the science itself, about these sort of science and knowledge issues, how do we know that science is true? The assumption that we make, of course, is that science is true. It's not like other fields of study. Science is true because it's about facts, and there are the facts, and you live with the facts, and there you go. That's an assumption that we all just tend to make, and everybody sort of makes. And in doing that, we reduce the universe to something that it really just isn't. We, by and large, in fact, almost all the time, we've not been introduced to the universe the way that it actually is. This is the universe of Albert Einstein, of Max Planck, of Niels Bohr, of Werner Heisenberg, in our modern times, of Stuart Kauffman, of Paul Davies, of Stephen Hawking, what's his name at Oxford, who I can't think of his name right now, that works with Stephen Hawking, and Roger Penrose, there we go. It is a world it is a universe that is so much more fascinating and baffling, and as Eddington says, yes, it is not only stranger than you imagine, it is stranger than you can possibly imagine. So we talk about relativity, we talk about special relativity, general relativity, we talk about black holes and Big Bang. And even when you get to Big Bang, even when you get to just special and general relativity, people have heard of these things, but they just, in general, and I mean from infancy all the way to death. People just kind of don't know what they're about. They've heard of them, but they don't know what they are. They don't know how they play out. They don't know. It's not that they don't know the math. They don't know the concepts. Right. So you talk about special relativity, and that leads into general relativity and space and time doing weird and bizarre things. And I mean, you can tell I'm getting passionate about it already. It's just fascinating. It's just fascinating. And it's fascinating in the sense that you as a philosopher, and I as a guy that talks about sort of philosophy of science and knowledge issues with respect to science, get excited about, because it shakes up people's paradigms. They have a certain paradigmatic way that they look at what we call this thing, life, the universe, and everything. They have a way that they look at things that turns out is not only just incomplete, but almost tragically incomplete. And when you complete it, when you take Newton, you complete Newton, and you learn that the universe had a starting point in space and time, and that gravity works differently than anybody would have ever thought. And you just go down that path to quantum mechanics and all the rest of it. It is just fun as a teacher. We're both teachers, so we know how this goes. Yes. To take a classroom full of people and just captivate them, to capture their minds, to capture their imaginations, to frustrate them, to take them to places where the brain can't go. One of the assumptions we make, of course, is that our brains can understand everything, and relativity, and particular quantum mechanics, all of a sudden we begin to see that, we can't understand these things. We can talk about them, but our brains just can't go to the places where these things demand that we go.
So you like to take people to the Gold's Gym of their mind. Is that what you're about? I mean, and why this particular area? Why this particular field for you, Andy?
It's probably my own personal history. I was a math teacher. I was teaching in Switzerland, and I don't know if you've ever been to Switzerland, but in January, in Central Europe, Switzerland is just like the rest of the countries, the weather's just sort of appalling. Christmas is gone. You can't go skiing except on the weekends, and it's gray and drizzly and drippy and hideous, and it's a long time till you get to summer. And so my classes were kind of sitting there, dying. We're just dying because you're doing algebra and geometry and whatever happens. And I just read Brief History of Time by Stephen Hawking, which is a great book. Then I read a book by Einstein himself, short little book on his own theories. And I thought at a point in January, what I'm going to do is I'm going to talk about relativity to these kids, to my students. And I'm just going to give them an Einstein day. And so I said, okay, tomorrow's Einstein day. You don't have to learn this. You don't have to pay attention. It's not going to be on a test, which every student loves to hear. Not going to be on a test. And I say, we're just going to come in and talk about Einstein. And so they sort of came sauntering in, kind of like relieved that they didn't have to know anything. They didn't have to actually pay attention. And they went out at the end of 50 minutes just buzzing, just enthralled with the ideas that Einstein revealed to us via his mathematics and the concepts that he showed to us. It was life-changing. It was paradigm-shattering. It was just fascinating.
I know some in our audience may be thinking, Einstein, you're starting to put me to sleep. He's so far out there, I can't even compete. I can't even stay up. How do you make it come alive for the average person, Andy? I mean, why? And why do you do it? Why are you so passionate about this particular arena?
Well, you stay away from equations and graphs and the stuff that you have to learn eventually, but you don't have to learn initially. And what you do is you tell stories. And so really I describe myself as a storyteller. I tell stories about science, about the history of science, about the people of science, but really much more about the concepts of science, what the concepts are all about. And so when you talk about Einstein, you can captivate them with a story. You say, okay, here's the story. We take two people from the audience, we take a guy and a girl, and we marry them off, to which is always to great hilarity, and everybody's laughing. And then they go on their honeymoon, which of course is naughty, and you shouldn't, everybody gets embarrassed. And then they come back and they're pregnant, and oh my gosh, we all giggle because they're pregnant. I don't know why, but we do. It's it's a natural thing, but kids just giggle about that kind of thing. And then she gets in a space program, and you send her off into space for 35 years. at 90% of the speed of light, and she comes back, and she's 20 when she leaves. She comes back, she's 55, and she looks around for her husband, and she finds this wrinkled old crone standing at the bottom of the ramp there at the spaceport, and he's 90 years old. He's aged 70 years while she's aged 35 years, and then her kids come up, and the kids are 70 years old, and if, as most audiences have not, as most students, even most teachers have not, they look at you and you get your first great response. They go, "What?"
Yes.
How are the children older than the mother, and how is he 90 years old? And you say, well, this is what the special theory of relativity does. So you start to enthrall them you captivate them with these stories about the way science works, and then you do a little bit of explanation. You show them a little bit of math, maybe a graph, and then you show how it plays out, and that's cool. And then you go to the general theory, and all of a sudden, space and time are bending and warping, and you got black holes popping out, and you tell stories about these things, and it's hard not to get passionate about it because it is the place that we live, and I guess that I also feed off of the passion of the audience, the interest of the audience. If they go to sleep on me, then I'm not quite as good.
Well, I've seen you 3 times, Andy, and that's probably far from the truth of students going to sleep. Students in my philosophy classes are still buzzing about your particular seminar. And I think, why does that happen? And again, I'm a philosophy guy, and we have in many chapters of an intro book, or philosophy of science. Why should we ask the deeper questions about science? And doesn't it always give us the truth? Doesn't it always give us the facts? Why should we be questioning science?
Well, obviously that's an interesting and controversial place to go, and the word controversy is key there, because I think controversy gets people involved in the process. If it's just a normal kind of ordinary, let's dissect a frog kind of not to
We've all done that.
not to diss dissecting frogs. It's important, and sometimes I talk about dissecting frogs. But when you talk about the fact that time is different, time passes differently at the top of your head than it does at the bottom of your feet, it's counterintuitive. Dissecting a frog, you expect to find frog innards in a frog because you've seen pictures of frog innards, and we've all watched, and so there you go. And kind of looks like humans. They got stomachs and hearts and spleens and all this kind of stuff going on. So it's not that much of a surprise. But when you discover that time passes more slowly at the bottom of your feet than it does at the top of your head, you have no way to have had any experience of that. And your question was, what is the evidence for that? Because that doesn't make any sense. That's baffling. That's just bizarre. And you say, well, all you need to do is take 2 really good atomic clocks and put one at the top of a tall building, one in the basement, and there you are. The evidence is right there.
Why should we care about this, Andy? I mean, what's the practical? What would be the difference in our lives if we knew this or not?
I've been asked that before, and I've forgotten completely what I said. No, it's, for example, quantum mechanics is a great. In fact, let's put quantum mechanics and relativity together for a minute. Okay. I've had kids say, "Why do I need to know that time changes? And why do I need to know all these stories about particles being in 2 places at the same time, and cats being both dead and alive, and all this weird stuff? Why do I need to know this?" And I say, well, take out your cell phone here just for a minute and look at it. And I go, all right, now you got GPS on your cell phone? And they go, yeah. Does that work pretty good? Yeah. Do you like GPS? Sure. I can find my way to restaurants and Gold's Gym or wherever I want to go. And I said, well, the only reason the GPS works is because of the general theory of relativity and quantum mechanics.
Now we're talking.
Now we're talking. And then you say, and there's your computer, and there's your iPod and your iPad and your droid, and all the electronics that you got work because of quantum mechanics. Your GPS satellite systems, you got a satellite that's traveling above the planet at however many miles, a couple of 100 miles up there. It's at a certain distance away from the center of the Earth, and so time is passing differently because it's different distance away from the Earth, and because of the speed that it's traveling. So you've got general relativity that's working in with your GPS system to be able to tell you accurately where you are. And then the only reason that electronics works, it's all quantum mechanical. Every electrical engineer, electronic engineer, everybody works with computers, with any kind of digital anything is working with quantum mechanics. It's the only reason that it works at all. is because of quantum mechanics. And so it becomes something that we didn't know that we needed to know, didn't know that we didn't know, and it actually is the way that everything is put together.
I've been to, like I said, a couple of your seminars now, and I've seen this shift that happens in the middle of your seminar. You start out projecting a pretty static universe as we've come to know it throughout the years, but then this amazing shift kind of happens halfway through. You've been alluding to it today, theory of relativity, quantum mechanics. Tell us a little bit about why you like to do this shift in the middle of your presentation.
Well, again, it's captivating. It captures the imagination. People wake up and start to listen because things are not the way they expected them to be. The classic way that we look at the universe is that it's a Newtonian universe. It's based on Newtonian physics. Starts off with the universe being infinitely large and infinitely old, an assumption that science began to make at a certain time, and it just persisted, and up to Einstein's time, everybody knew the universe was infinitely large and infinitely old. And most people right now, if you said, has the universe always been there? And they would say, what do you mean by that? I mean, okay, the empty space. Let's don't talk about the galaxies and the planets and stuff. Just the empty space. And they'd say, oh yeah, that's always been there. You know, that's always just been kind of been there. That's the way it is. Right there, you know, general relativity comes along, Big Bang comes along, and all of a sudden, it's not that the dirt in the universe, the galaxies, the stars, the planets, not that they had a starting place, but that the universe itself, space and time, had a starting place. Okay. That space and time came into existence about 13.7 billion years ago in a moment that was one of the most incredible shifts. I want to go as far as to say it's the most incredible shift in scientific thinking maybe ever, because we went from an assumption that it had always been there, was just static and uninteresting basically, to all of a sudden it had a start, the clock started ticking, that space came into existence, time came into existence, the laws of physics came into existence, energy came into existence, matter came into existence, all via general relativity, quantum mechanics, and the laws of physics that made everything happen. And that is something that I think, I mean, it's fun. Yes. It's also a huge shift in the way that we think about things. It's a shift in the way that science thinks about things. Yes. And a shift in the way that each one of us thinks about things, because now all of a sudden we're talking about origins. Yes. And origins are a philosophical, a theological, a metaphysical, a human issue, not just a scientific issue.
It's in the 4th chapter of our intro to philosophy text. It's entitled The Search for God. And I wanted to, it's an important question that we ask constantly within philosophy. Is there a God? And if there is so, what are the implications of that God in the world today? Particularly, and for you, in a cosmological sense. I want to quote something from your book here. This is from your book, Quantum God, Fractal Jesus. You said, it has emerged from the beauty of the math and the physics, according to the way God planned for it to be, but not a plan like we might expect, and our limited focus and understanding, but a plan with both structure and unpredictability, with rules that would give the result the plan was designed to produce, but not within a tight construct or a narrow range of possibilities, but a broad, sweeping, cosmic, near infinity of gorgeousness. Now that is a quote. Do you want to elaborate on that?
No, it's pretty good. I'll just go with it. Yeah, no, it's all right. It's all right. It's a question that, I mean, obviously, again, controversial. It's a controversial question.
Yes.
And as I travel around the world, I discover that in different parts of the world, it occupies a different level of controversy. Not quite so controversial in the Far East. It's a question about which we can talk with students and teachers. I had 4 trips to Asia this year, and so I spent a lot of time with Asian students and Asian teachers, and Europeans and Americans and Westerners who were living out there. It's a similar sort of question from response from, say, Latin Americans and Africans. It's a question about which you can talk profitably and have an interesting conversation. Western Europe and the United States, it's a question where it's so controversial that it's almost to the place right now where we're afraid to have that conversation, which I think philosophically is an interesting place.
Yes.
It's a great question. Not so much can we talk about it, but why don't we? Why are we afraid of talking about it when other places, which are maybe even less spiritually minded, less religiously oriented? So I had 2 trips to China this year. I've done more schools in Shanghai than I've done in the entire United States. And you would not point to China as being a deeply spiritual sort of place, certainly not in recent history. So I think that's an interesting, a really interesting question. The ultimate answer, I guess, is that science is having this conversation.
Yes.
The reason we have this conversation is because the scientists themselves are having it. They all look at the same evidence that I talk about at great length, sometimes 12 hours worth, in my time with students and in schools and with teachers and even parents and family members. And when we look at all the evidence, we get to the end, we find quotes from the scientists, and the scientists are saying, they're dividing themselves into 2 camps, but they don't divide themselves into 2 camps, because you find somebody like Steven Weinberg, who's part of the New Atheism movement. He's a brilliant man, very articulate, very charismatic, great guy to listen to, very quotable. And on the one hand, he will say that there's no evidence that there's any reason for humanity in the universe. And on the other hand, he will say, something like, I'll have to throw out the Anthropic Principle we haven't really talked about, but he'll say, we may end up using the Anthropic Principle, because the universe is such a wonderful place to describe the wonder that we see in the universe. So he on the one hand, he wants to be very reductionistic and say, there's no evidence, but on the other hand, the universe is just so much cooler than we allow it to be sometimes. You've got some people who are pretty strongly in one camp, and others who are fairly stronger in the other. But these are guys that hang out together and spend their time together. They do their research together, and they have this conversation. If they're having the conversation, and they haven't resolved it yet,
yes,
then I think it's not only fair. I think it's expedient upon us,
yes,
to have the same conversation amongst ourselves, using and looking at, utilizing the evidence that the universe provides us. Not proof of anything, but evidence that can be interpreted in several different directions.
This is something that we desire for students here at Pikes Peak Community College, to go deeper in their philosophical assumptions, their inquiries, their reflections. We want to create a safe place where students can fearlessly and critically investigate some of the biggest and thorniest questions of our day that are controversial and important questions. So I think that's why we have such a good connection in terms of bring you back year after year. What are some of the typical questions you get from the audience, and maybe some challenges that you might get along the way? But what are students usually asking?
It's interesting that the questions that I get are, I don't want to say they're all the same, because there are lots of questions that I get, but they tend to focus on 2 issues. One of them is quantum mechanics, because quantum mechanics is so bizarre. Could
you just give us just a 15-second rundound of quantum mechanics?
I cannot.
It's impossible. Yeah. I know, but I like seeing you do the impossible.
Quantum mechanics is a study of very small particles, and very small particles have a different, I kind of want to use the word reality. They have a different way they interact with the universe than those of us who are made up of very small particles. Right. It's all about probability, and you can say it pretty simply, that a single particle can be in multiple places at the same time. You and I don't do that, and so there's a disconnect between the way that we experience the universe and the way that particles experience the universe. They can transverse the entire universe in a single instant, instantaneously, a bit of matter going far faster than the speed of light, which is not possible, and Einstein drove Einstein crazy. Among a host of other things that are interesting, the one that really is probably the most controversial, and yet John Wheeler at Princeton, the guy who named black holes, was at the Institute for Advanced Study at Princeton with Einstein and all the rest of them, one of the finest minds of the 20th century, died, I think, last year or the year before. Wheeler says it is the most fundamental, it is the most central core issue of quantum mechanics. It is absolutely fundamental to quantum mechanics to say that. And here's the most bizarre thing, and this is what he's talking about. He's saying that without observation, there is no reality. without some sort of interaction, apparently between humans or intelligent beings of some sort, there is no reality, that the universe exists in a quantum state of superposition, where reality doesn't actually exist, up to and including the universe itself, unless there is some sort of an observation. Defining observation is problematic and controversial. Is it an observation? Is it a measurement? They divide themselves on that one. But what it does is that it's a corrective. In fact, it's almost a cancellation of the Copernican Principle. And the Copernican Principle says that humans aren't special, the Earth is not special, our solar system is not special, that we are just beings that happen to be here by random chance in a vast and indifferent universe. There's nothing special about us, and we operate on that principle that there's nothing special about humans. Now, I would be the last to say that there's nothing special about the rest of the universe. I have a whole session on complexity theory where we talk about how much more complex and interesting and intelligent animals are, and particularly in groups, than we would necessarily understand them to be. But there is a special place that humans seem to offer, and you can define it as being having the role of observer, that we observe the universe, and in that observation process that reality is created. That is controversial, and nobody likes it much, and everybody disagrees, and yet it doesn't seem to go away, and it becomes part of our discussion.
Can you see that, how do you feel about, in light of what you just said, how do you feel about then the philosophical reflection that's needed behind our science-filled presentations that are going on at this very minute all across the country?
You know, it's an interesting question. I'm gonna hurt you as a philosopher here right now.
No problem.
I have
we can take it.
I have what passes for what might pass for a minor in philosophy, so I have some credibility. Not as much as most, but more than some. I don't think that you can really meaningfully talk about philosophy without having a deeper understanding of the way the universe is put together physically. I don't think you can talk philosophy without understanding the way that life and the universe and everything actually are. Otherwise, you are spinning webs in a vacuum that aren't necessarily connected to anything. And they're very nice looking webs, but unless they're connected, they don't catch bugs.
So are you saying that the humanities needs science, science needs the humanities? It would be good if we could just learn how to all get along, or at least appreciate each other's disciplines? What are you saying?
I think that the way that the physical universe is put together would inform our attempts to understand that universe. And absent some sort of an understanding, that implies you can understand it, which would be a mistake. Absent some sort of a familiarity in a narrative sense with the stories of the way the universe is, I don't think we can come up with a meaningful way to talk about our role in that universe. I think we then just create complex, fascinating, but ultimately detached stories about what our role in the universe is.
Andy, we just have a minute or two to wrap up here. Any final words that you wanted to share with us, or thoughts, something you wanted to leave us with today?
I continue to learn. I continue to read, and if I had any words of advice for anybody, I would say just go out and do some reading on the way the universe is, and read scientists, not so much. I'm not even. Yeah, I think it'd be fine to read my books because basically it's all based on what the scientists say. But there are a host of other books, a lot of them on my website. I've got a long bibliography. The best ones are noted there. Read about them. What you'll find is that we all come to a different set of conclusions about the way the universe has meaning. Not so much about the way that it works, but the way that it has meaning. Get out, read. Skip the big words. I've got books where I've read the first sentence and the last sentence of every chapter. That's just fine. Do that.
Do something.
Do something.
Learn some more. Do you have a website, tokseminars.org? So that's where another place that you can go to. Andy, we've really enjoyed our conversation and with you today, our interview with you today. The life, the universe, and everything. Thanks so much, Andy, for coming.
Thanks for having me. It's been a great pleasure.